What we have going on with this problem is getting you to understand the fundamental counting principle and what we call permutations. So we've actually done a few of the fundamental counting principle problems in the previous one. We just didn't formalize it, so that's why it's bolded right here. So if we have a coin, so just a heads or tails coins, and we're trying to make a tree diagram out of it, so we flip that first. Actually, the order doesn't really matter. I could do it the other way. And then we have the rolling of the six-sided die. So 1, 2, 3, 4, 5, 6. So there's 6 options here, and then 1, 2, 3, 4, 5, 6 options here. I'll just write that out. That the total number of outcomes would be 6 plus 6, which is 12. But they don't want you to think of it that way. What they want you to think about is how there were 2 different scenarios. There were a heads or a tails, so 2 for a coin, and then 1, 2, 3, 4, 5, 6. So what can I do? What operation can I do between 2 and 6 to get 12? You multiply that, and that's why the order didn't really matter how you do the problem. Like maybe you roll the dice first, roll the die first, and then flip the coin. Well, then you have 6 options first. Maybe I'll just show that in a different color. 1, 2, 3, 4, 5, 6. And then each one of them has heads or tails, heads or tails, heads or tails. There's still 12 options at the bottom. And that's what this thing is. It looks confusing, but if you want the total number of outcomes for an event, and the event is broken down as several different events, you take the number of outcomes for event 1 times the number of outcomes for event 2, so on and so forth, all the way till the end. So in a problem like this, I've seen students try to come through every single possibility, but it gets obnoxious. And this is an example of an obnoxious problem where you get a daily order at a cafeteria of 1 drink, 1 salad, 1 entree. So if you look at the menu board, we have 5 choices for the drink. We have 4 choices for the salad. And we have 3 different entrees to choose from. By this rule up here, you multiply. And I don't care how you multiply. If it was up to me, I would do 5 times 4 first, which is 20, times 3 to get you 60 choices. Let me pick a bolder color as I move forward. And what we have next is getting you to see the number of these 4-letter codes that begin with 2 vowels. So we're choosing letters from this word, hyperbola. It's a math term. You may not have heard about it yet. Without replacement. So that's important as we're looking at this problem, to create a 4-letter code. So I think what I would do is put down 4 of my blanks. This is just a visual for me. I don't know if it's even helpful for students, but that's what works for me. We want a 4-letter code. So determine the number of these 4-letter codes that begin with 2 vowels. So I'm assuming you know what vowels are. I suppose if you see a problem like this, you don't know what a vowel is, you could ask. A, E, I, O, and U, and Y is also a vowel in this problem. So there's 1, 2, 3, 4 vowels. So we want to start with a vowel. So we have 4 options. And that's where this gets tricky, because then students want to do 4 vowels for the second one, because we want 2 vowels, but it's without replacing. So let's say this very first option, you choose A. Well, now you can't choose A again as you're picking the letters. You only have 3 vowels to choose from. Okay, so let's say we choose E. Well, we're still not replacing it, but now the next one could be a vowel or a consonant. So that's why as I look through, there's 1, 2, 3, 4, 5, 6, 7 options for the next one. And then let's say we chose, I don't know, B. Now we're down to 6 options. And this time I'm not going to torture you and say you should be able to do that in your head. I think you do 4 times 3 in your head, but then it might get tricky to do times 7 times 6. But you do get the correct answer of 504. And I'm more concerned about you getting the right answer. But if you reread the problem, it's codes. So there's 504 different codes in this word that would have 2 vowels that you cannot replace. So you can't use the same letter twice. Maybe I should write that out. That might help some students. Cannot use the same thing twice. And I'm saying thing because we might see a problem in the homework or later in the notes on the test where we're picking out marbles without replacement. So that's why I'm saying the same thing. In this case, it was a letter, but in the future probably could be a marble. Could be a card in a deck of cards. We're also going to talk about what are called permutations. Okay? And what we're going to do for a permutation, at least this first one, is it's a special kind of fundamental counting principle. And you can actually do a few problems as permutations as the fundamental counting principle. So this might be helpful for you. So we have the word cat, and we want to choose 2-letter codes out of these without repeating the same letters. So list all the different 2-letter codes. So that's where you might see me use roster notation, where the 2-letter code could be CA, which would be different than, well, let me just go through what I would do. I would do CA and then CT, and then I would go to the A. Let's say we pick A first, and then it could be AC. And that's what I was about to say, is CA is different than AC, so the order matters. That's going to come in important eventually, if not today, in permutations. Okay, so AC, then AT, and then I would go to the next letter, which would be T, and then go through all the options, TC and TA. So I think you can tell that we have 6 options. Now, if we did the fundamental counting principle, what we might do is say, okay, well, we want 3 letters, and we're going to, it doesn't matter what we choose first, we'll just choose one of those 3. Let's say you choose T first, well, now you're down to 2 options. And, well, at this point, it doesn't even matter which one you choose, but 3 times 2 gives you 6 codes. Really, that word doesn't really matter. I'm curious if you get the right number. But let me explain what is a permutation. Ooh, that just did not show up very well for me. Okay, this is supposed to say NPR, just like this. And what you do for NPR, NPR is equal to, you do the top number factorial over the bottom number factorial. Now, what you could do is, you could probably see from the previous problem, I'll explain this, the exclamation points in the word factorial in a moment. But what I'm going to do real quick is show you that you could actually do this problem, because the 3 in this problem tells you how many spots you have, and you take the 8 and you multiply down this way. Now, let me take a break from that for a second and explain these factorials. What factorial is, and I'm just going to use n factorial, is you multiply that whole number by the next one that's smaller than it. And then you multiply by the next one that's smaller than that one. Kind of like how I did 8. 1 less than 8 is 7, and then 1 less than 7 is 6. And you go all the way down until you multiply by 1. Yeah, so let me explain in a different color how you could do that notation. Is that's the same thing as 8 times 7 times 6 times, whoops, I gave you the wrong formula now that I'm looking at it. Is what you actually wanted to do, and I do apologize, you're probably rewriting this a couple times, is that second one is supposed to be actually n minus r. So it's supposed to be 8 minus 3, which is 5 factorial. And so you could cancel out all of those 5, 4, 3, 2s, and 1, and you're left with 8 times 7 times 6, which is, well, I would use a calculator. So just real quick, with the calculator, I know this looks like magic because I just pulled this straight up on my computer, but how do you get NPRs if you hit alpha window, the 7th option down, and you can type it in, 8P3. There you go. So I'm perfectly fine however you want to solve this next problem. Just to show you, it would be 15 factorial over 13 factorial. And sometimes what you'll see is teachers get lazy all the way down to 1, because on bottom you have a 13 times 12 times 11 all the way down to 1, and all of those pieces will cancel. 13, 12, all of them cancel, which is why the other method I showed you worked, where you could write down 2 blanks and then 15 times 14. And again, I'm fine if you're using the calculator, because that's kind of tough to do in your head. I'm sure you can figure it out, but that's okay. Or, what's the other way? Alpha window, the 7th option down, 15P2. It's 210. Now, the downside to the next one, if you're going to do the rule that I have up here, is it looks like it's 4 factorial over 0 factorial. Now, kind of a heads up, this might seem weird, but it is a rule in math, and there's a reason for it. We just haven't learned it yet. So the 9th option is a factorial. Whoops, I meant to put 0 factorial is always equal to 1. That seems weird, but it has to be true. And the reason why it has to be true is if you do the permutation the way I've done the previous problems, we have 4 options. It's 4 times 3 times 2 times 1. We're going to get the right answer. 4 times 3 is 12 times 2 is 24. So in this problem, where we have 10 runners and we're trying to get first, second, and third, this is you could do a permutation, but you could also do the fundamental counting principle. And I'm good either way. So if you have 10 runners that have 3 positions to get, and here's the other thing, is order matters. That's going to get confusing when we get to a later problem. If you want to do the permutation, 10 times 9 times 8, and sometimes you might even stop at 7 and just write factorial, because 10 minus 3 is 7 factorial, that those 2 things will cancel, which confirms how I did the fundamental counting principle before. I would probably just do this in my head, because 9 times 8 is 72, times 10 would give me 720 ways that they could finish first, second, and third. I'll put another equal in there, just to show you there's 2 different ways of doing this. And then here's another one, and the key here as to why it's a permutation is the different orders that Darla can put 12 songs in a playlist and listen to all 12 songs. So if you're going to do permutation notation, it would be 12P12. And in other words, it's going to be 12 factorial over 0 factorial, which remember that that's just going to be 12 factorial over 1. And so it's up to you if you're going to use a calculator. I would definitely use a calculator, though. Is if you hit 12 factorial, would be the same thing as this if you did 12P12. A ridiculous number of ways of getting the right answer. I'll just copy this over to keep this somewhat small, short of a video. I know I'm at my time limit, but you should be ready for the homework now.